Welcome, everyone. Thank you for joining us today. My name is Odette Hines, and I'll be your moderator for the webinar entitled Diving into the World of the Smallest High-Res LiDAR Camera, the Intel RealSense LiDAR Camera L515. Your presenters today will be Ferdinand Reitze, who is a business development and portfolio manager here at Framos. Ferdinand joined Framos in December 2019, and prior to that, he spent 3 years in the Strategic Business Development Department at Intel, where he had a focus on drones. He now manages the Intel portfolio here at Framos. Our next presenter is Chris Bernard, who is a product manager in the Intel RealSense Technology Group. He's been working with depth camera technology since 2014. Within the Intel RealSense Group, his other roles were engineering manager, marketing manager, and customer enablement. He holds a Global Executive MBA from St. Mary's College of California, a Master of Science in Computer Engineering from North Carolina State University, and a Bachelor of Science in Mathematics from Roanoke College in Salem, Virginia. Before we start today, I want to provide you with a few housekeeping rules. All participants are in listen-only mode. If you have a question during the webinar, please type them in the question section in your Zoom control panel, and I'll ensure that they're answered at the end of the webinar. If we do not get your questions today, we'll send your answers to you a few days later. The on-demand version of the webinar will be available within the next few days. We will ensure that that is sent to you as well. If you require a conversation or a demo, please ensure that you put that request in the question section of your Zoom webinar control panel, and I'll ensure that they're directed to the presenters at the end of the webinar. Now, without further ado, I'll pass it over to Ferdinand. Ferdinand?
Hi, everybody. Just give me a second. I'm experiencing some challenges with my setup here. I hope you guys can hear me. I'm starting to share my screen now. So thank you, Odette, for the introduction, and thank you all for joining today's webinar about the Intel RealSense L515. We will go through the webinar talking about the different depth sensing technologies that you encounter on the market today. Obviously focusing on the L515's time-of-flight technology later on. We talk about how it works, the principle, the technical details, the benefits of MEMS-based solid-state LiDAR over other conventional time-of-flight technologies, and data presets and how to use it, and at the end briefly touch a couple of use cases. Okay, give me a second. There seems to be an issue with the screen sharing here. My apologies for that. So now it should work fine, hopefully. Please let me know if it's still the presenter screen. Very good, then let's continue. So first of all, let's have a brief look at why depth sensing in general. For many of you, this may be a repetition, as you already made your first contact with depth sensing, maybe even with the RealSense technology. But for those of you that are new and looking to depth sensing, I will try to briefly position it and how important it is within certain verticals for automation. Automation is a key driver within many industries and verticals, driven by more processing power that became available over the recent years, the low power of those devices, power requirements of those devices, advances in AI and machine learning. Those all are key drivers currently in the automation. And in the past, automation was reserved for simple, highly repetitive tasks and was pretty expensive. But today, with all those advances in the aforementioned different fields, more and more complex tasks can be automated. Often, we talk about automation. Those requires the devices that need to be automated or processes that want to be automated. The machines and devices need to become aware of their environment, either to detect and interact with other objects or humans in the environment, avoid collisions, ensure safety, measure objects, dimension objects for quality assurance or volume estimation, weight estimations, and things like that. Or finally, if you put everything together to navigate within a certain environment. And the goal is, as you can see in the center, often to process optimization or to automate existing processes or completely new ones. Let's have a look at some different optical technologies that are available to do depth sensing and how the L515 fits into that environment. First of all, other technologies such as radar or ultrasonic are not listed in this overview. And within the optical technologies, you can distinguish between active and passive technologies. Passive, depth from texture, done by knowing features that are given in a scene, how big they are, and then apply that know-how to also calculate depth of surrounding objects in that scene, or applying AI models to have a deterministic approach from a single image, extracting depth information. Or you have passive stereo setups. How stereo works, we will also cover a little bit more in detail after this slide. The D400 series from the Intel RealSense portfolio can be operated as passive stereo if you deactivate the infrared projector. There's also a passive module available, but in general, active systems are usually superior to passive models as they enhance scene or provide additional functionality to have a more robust depth calculation. You can distinguish basically in the active technologies between technologies that are based on triangulation and other technologies that are based on time of flight. Within triangulation, you have active stereo, structured light, and coded light. D400 from Intel is, again, it's an active stereo-based technology. We as Framers offer a more industrial version with an Ethernet interface of that series. Coded light, Intel has the SR300. It's basically structured light, but adding, modulating the structure that is projected over time. And in the structured light, you may have heard of the Kinect or the new Intel product, the Face ID, that is also based on structured light. With time of flight, you distinguish between direct and indirect. We'll cover that in more detail later in a slide as well. Within both, you again distinguish between scanning-based solutions and flash-based solutions. Also on that, I'll have a little bit more later in the slides. For example, the new iPad Pro has a flash-based direct time-of-flight technology in there. Scanning-based is a typical Velodyne LiDAR, for example. And now to position the L550, it's an indirect time-of-flight camera that is scanning-based. Now, an important learning when talking about depth sensing in general is that there is no one-fits-all solution. Each technology comes with advantages and disadvantages that render it good for certain applications. So you have to know your requirements to choose the best suited for your application. And we at Framers can also support there to help make that decision. Let's have a brief look at the working principle of the three most common technologies that you will run across, starting with coded light or structured light, where a known pattern is projected onto a scene using a single imager setup. The disparity between the known pattern that is projected and the observed deformed pattern can be used to calculate the depth for each pixel. Advantages are usually in the very low cost of the setup. It's again based on a single imager and a simple light source that projects the structure. But it also comes with disadvantages when we talk about range. As you can imagine, to project a pattern in direct sunlight, for example, over larger distances would require a very powerful light source. With stereo, this is probably one of the most common. Sorry, back to coded light. You have a lot of these in structured light. You have a lot of these, for example, in your cell phones to unlock from the lock screen, for example. Stereo, on the other hand, mimics human vision. It's based on two images that are set apart by a baseline. The higher the baseline, the higher the accuracy that you can get, as a rule of thumb. And each imager captures the scene slightly different from a different position. And the disparity between the captured images can be used to calculate the depth map. The technology is very robust to varying lighting conditions. It struggles, however, when it comes to homogeneous surfaces like completely white or single colored walls. That's why usually we talk about active stereo, where you have an additional projector, usually infrared, that adds texture to those homogeneous surfaces that can be used to calculate the depth better. It's usually inaccurate, from talking about accuracy, less accurate than structured light. But depending on the setup, you can also get devices that work in a sub-millimeter space. Obviously, these come at a cost. However, as mentioned, they are very robust when it comes to changing lighting conditions. Last but not least, let's have a look at time of flight, because this is what we want to talk about here today. Various technologies are available that use the same principle. As mentioned before, radar, ultrasonic use the same principle, which is you send out a signal and you measure the time it takes from emitting the signal to receiving the reflection of that signal. And by knowing the speed of the signal, in the case of LiDAR, the L5.5, the speed of light, you can easily then calculate the distance between the camera and the object that was hit. The LiDARs usually, and time-of-flight cameras in general, are very stable when it comes to calibration. But also in the past, they have been pretty expensive. Just recently, time-of-flight cameras, and now with the F5.5 LiDAR as a LiDAR, the advances in technology brought it into an interesting price range for a lot of applications. It's if you look at the pricing, the cost comparison, this is based on the cameras within the Intel portfolio. For every characteristic, for every feature compared here, you will find within each technology cameras and technologies that outperform or underperform. So you will find very expensive stereo cameras, but you will also find very good ones with a perfect price-performance ratio. Now, looking at time of flight in more detail, let's start with direct time of flight as a basis for the technology. It's based on transmitting a pulse, receive the reflection, and then measure the delay between the emitted and the received signal. And knowing the speed of light, as mentioned before, it's a very simple calculation of the distance to the point that it is measured. The challenge here with direct time of flight is the higher the sampling rate, the higher the accuracy you can achieve. For example, if you want to achieve a 1 millimeter accuracy, you have to be able to recognize and sample at a speed of 3.3 picoseconds. So this is pretty immense, and that's why with direct time of flight, it's very hard to realize a camera such as the L5.5. On the other hand, indirect time of flight uses the same principle of measuring a delay, but instead of a single pulse, you transmit continuously and you also receive continuously. And then you can use correlation algorithms. And in the case of the L5.5, this is done on multiple frequencies to compare it to the template that you've emitted and measure the delay in the phase. And you can do that when you do a cross correlation, you will get such peaks, and with such very easily recognizable peaks, you know this is the best match, the best accuracy that you can get for this specific point. And this is also the value that is then transmitted. The benefit here is it's independent of the sampler frequency. So you can achieve 1 millimeter accuracy without being able to detect a delta of 3.3 picoseconds. Now, how is the L515 set up? We talked basically about three functional areas. Well, first is the transmitter, then the receiver, and the depth module. The transmitter consists of a laser diode that modulates at 500 megabits per second a continuous code, and a 2D MEMS system that moves the laser across the field of view. The receiver is a single omni receiver. It's based on an avalanche photodiode, an APD, and it collects actually the light of the entire scene. So it doesn't follow the laser beam, but it collects photons coming in from the full scene. The depth module, on the other hand, is basically an ASIC, a visual processing unit, that does the correlation and calculates the depth based on the aforementioned correlation and applies post-processing filters. Functional components in this block diagram, as mentioned, you have the BPU. In the projector module, you have a mirror controller that controls how the MEMS is oriented. You have the laser diode and a driver for that. The receiver is the APD and an analog converter, and a transimpedance amplifier for the signal gain. Also, you have flash storage and a USB interface. And again, on the BPU does the correlation, the calculation, post-processing, and sending out the processed image to the host. Going a step further, how does the L515 scan a scene, and how does this then lead to depth information for per pixel? As you can see in the illustration on the left, the laser beam is skated across the vertical axis from left to right onto the scene. And the blue lines in the graph on the right represent how the beam is moved across the entire field of view. While the laser beam is scanning the scene, the photodiode continuously detects photons across the entire field of view. And finally, at the red dots that you can see here, these are measurement points from where the calculated depth is then put into the depth map and transmitted to the host. It's important to understand here that there are no interpolated pixels. So every point that you see is a real measurement, because the system continuously transmits, receives, and also does the correlation continuously. Now, since the basic principle is clear, let's talk about some of the benefits. And one big benefit is that the L515 with its scanning-based setup is more robust compared to multipath effects. And it's a common challenge, multipath, for time-of-flight systems. Multipath, for those who are not aware of that effect, it's the effect that you don't just only receive a reflection from the point that you are actually targeting, but that you also receive reflections from other surfaces in the area where the light was reflected indirectly to. With flash-based solutions, you illuminate the whole scene at a single time, and you are also capturing the scene at the same time, giving you a pretty long exposure time. And this can increase the effect pretty much compared to a scanning solution, where each point is targeted individually, and it's much easier to distinguish between the desired reflected signal and reflections and signals coming in from indirectly hit areas, so the multipath effect, so to say. This is further enhanced on the L515 by performing the correlation on multiple frequencies. That's additionally lets you filter out multipath effects more efficiently. The next benefit, specifically to the L515, is the low signal to noise ratio that it can work on. It actually can work on the negative signal to noise ratio. SNR is is basically when flash-based solutions, every system has a base noise on its own. And for flash-based systems, conventional time-of-flight cameras, where you have a typical sensor array, you need to get signals that are above the noise of the system to recognize them and then calculate the depth. Using correlation, and especially also on multiple frequencies, it is possible to run a very low signal to noise, and the L515 can run at -6 dB and still recognize the peaks coming from the correlation algorithm that enable you to calculate the depth. Long story short, this really helps to run the camera at very low power consumption. The last benefit of the L515 that we're going to look at in this detail is the pixel shutter, as Intel calls it. This means that the scanning technology allows for an extreme short exposure time per pixel compared to a conventional time-of-flight camera that is based on a sensor array. If you use the VGA resolution of the L515, you have a pixel shutter or exposure time below 50 nanoseconds. And compared to a shutter speed of, let's say, 2 milliseconds on a regular time-of-flight camera, the exposure is around 40,000 times faster. And that gives you almost no motion blur, as you can see in this video. The fan's blades can be recognized very sharp, while if you look at the RGB image, which is basically a typical sensor setup with longer exposure times, you just see that big mess of a blur. On the other side, this scanning comes with a downside of rolling shutter effects that can maybe be observed on very fast objects, meaning that a fast-moving object can be distorted, sketched, or squeezed in the final image. Let's summarize some of the things that we just walked through the 515. Again, no interpolated pixels. Every pixel is a real measurement. And the projection angle, I haven't mentioned that so far, can be controls the field of view. Meaning, when you reduce the field of view, the image is not just cropped, but the MEMS controls the laser beam through the reduced field of view, and thus increasing the accuracy and resolution that you can achieve. Next up, the aforementioned short exposure times, which lead to that you don't have any noticeable motion blur in your final image, and the non-harmonic correlation on 64 frequencies, together with the overall scanning approach, make the system robust against multipath effects. And non-harmonic correlation on 64 frequencies also enables the operation in negative SNR. Together with a very highly sensitive large collection area, this leads to a low power consumption of the camera itself. However, this also comes with not necessarily the downside, but it makes it susceptible to interferences from other light sources that emit infrared light in the same wavelength. And therefore, the L515 is targeted for, and optimal for indoor applications at the moment. You can also encounter some jitter effects coming from the MEMS system, but those can be mitigated and removed with a temporal filter. Let's have a look at the different data streams that you can get from the L515. First of all, the depth map, which obviously is what everybody's looking for. Each pixel is a 16-bit integer pixel that with the SDK can be converted to a floating point. The maximum resolution is XJ with 1024 to 720 pixels. A little bit more on the next slide. Let's have a look at the confidence map. It's a second stream, and it's a time and pixel synchronized map of the confidence level for each pixel. Each pixel is a 4-bit value and tells you how strong the correlation was. A strong correlation delivers you a high confidence in the measured depth information and gives you is a high number, while a low number, 0, basically renders a measurement invalid with no confidence in the measurement. Additionally, there's an infrared map. This infrared map is generated from the reflected signals, so it's not an infrared sensor that covers that creates that map, and therefore, as you can see in the example image, it doesn't have a very good signal-to-noise ratio. It looks very there's not a lot of contrast in it, and based on that, since it's really calculated from the reflected signals, it's usually also limited in the range where you can get a useful map. You can use that to calibrate external cameras or biometric analysis. The range, as mentioned, is up to 4 meters approximately. Last but not least, the L515 has an RGB imager included with 2 megapixels. It's running at 30 frames per second. The color stream is independent of the depth stream, so the resolution and the frames per second can be controlled independently, but you can use the InterRealSense SDK 2.0 to project the RGB information onto the depth map and synchronize it via hardware to the depth stream. Going a bit into more detail on depth stream, the detection range is radial 9 meters at 80% reflectivity. Reflectivity is in general the number of photons that are reflected back from an object, and simplified, a Lambertian surface is considered a matte diffusely reflecting surface with which the brightness, the perceived brightness seems the same to an observer independent of his position and viewing angle. So a wall you can consider as a Lambertian surface, while water or mirrors are clearly not Lambertian surfaces. And objects with lower reflectivity can still be detected, but usually this comes with an impact on the detection range, or also with lower confidence values. With the various controls that you have in the InterRealSense SDK, and the presets given, the next slide, I'll talk a little bit about those. The system can be tuned to detect a wide variety of objects over a wide variety of dynamic ranges. And last but not least, the radial projection that is received, the radial 9 meter measurement is already projected onto a parallel plane directly on the L515. And this therefore reduces host computation requirements, as it's already done on the device itself. The illustration on the top right also shows a little bit how reflectivity impacts the range that you can achieve. If you cut reflectivity, if you cut the range by half, then you can detect objects with 20% reflectivity compared to the 80% of the 9 meter range. So the range is reduced by a square factor. The reflectivity reduces the range by half. Advanced controls, as mentioned, give you an option to further optimize the perceived image and adjust it to your specific needs, depending on long range, short range, high reflectivity or low reflectivity objects. And the presets that are given in the RealSense SDK are a good starting point. You have the max range preset, short range, low and no ambient light presets. And all those presets change 4 main parameters, which is the laser power, basically the emission power of the laser diode, the digital gain, the minimum distance, meaning from what point on measurements that are too close are rendered invalid. I'll have something more on that in a second, and the receiver gain. The max range setup is setting everything on full power, maximum gain to maximum, range to maximum. Well, the minimum range is set to the furthest distance, and also the laser power is set to maximum. It gives you the best chance to detect objects that are at the maximum range of the camera. But close objects will be, based on the settings and all the gain that you have set up, oversaturated and not providing good information. And that's why the minimum distance is increased to remove all those oversaturated areas. If the range is bigger than 9 meters, it comes with a drawback that you may see some ambiguity artifacts. But if you really want to achieve the maximum range, then this is the best setting to start with. Next up, you have the no ambient light preset. It's the same as maximum range, but the laser power is calibrated to avoid the ambiguity artifacts. It comes at the cost of signal to noise ratio versus maximum range. So when you want to improve the quality of the depth map and you don't have any ambient light coming in, you have controlled lighting conditions, then you may prefer this preset for maximum range. Low ambient light, a preset that helps to improve anywhere where other infrared sources may provide interfering infrared signals to the camera. Again, the L515 is targeted for indoor use, but if you have a window close by, then this setting may help you. The laser power here is back again on maximum, but the receiver gain is reduced to better distinguish between signals that the L515 sends out to infrared signals from their ambient noise from other sources. Short range, similar to low ambient, but it also, instead of the maximum laser power, you have a calibrated laser power, and it's really recommended when you have objects that you want to scan from 25 centimeters to 2 meters or close, in that range. Additional controls that you can see at the lower half of this slide enable you to customize the settings depending on your needs. For example, you have the confidence threshold that you can adjust. It's by default set to 1. You get a pretty good depth map, as you can see, with a high fill rate. But at the edges, you may have some areas where there's low confidence, and therefore the values that come back are rendered invalid, and you have those invalid edges. If you set the confidence to maximum, then only values with a very high confidence are transmitted. And as you can see of the same scene, it reduces drastically the fill rate. But the information that is received back, the depth values, the system has a very high confidence, so it's the most reliable depth map in terms of accuracy. Also, you have various post-processing and pre-processing sharpening filters. Lower sharpening leads to very noisy edges. Sorry, here's a mistake in the slide. If you increase the sharpening, then I'm sorry, that's correct. So if you increase sharpening, you have more noise, and lower sharpening leads to those smooth edges, but at the same time also with decreased noise. Another typical challenge and question that comes up when working with time-of-flight cameras, flash or scanning based, are interferences with other cameras or infrared sources. We covered interferences slightly previously when we talked about the indoor optimal range of use for L515. But those interferences are caused by the difficulty of the device to distinguish between the desired signal that it sent out on and receiving its reflection, and other signals coming from other cameras. It can be resolved by camera positioning, or by hardware synchronization. Let's look at camera positioning first. If you take the first example on the left, if you have the cameras facing away from each other, the chances of interference are almost non-existent because you don't get direct reflections back, and you can probably easily distinguish between the signals you want and the ones you don't want to have. As soon as you have the cameras facing each other, even with the objects in the middle, every now and then you may encounter interference when the field of view is not obstructed by an object. And last but not least, if you have cameras set up in the same direction in an overlapping field of views, you can be sure that you will encounter high interference if you don't use hardware synchronization. If you look at the bottom two images, now you see the example C with two LiDAR setups and without hardware synchronization. You can easily see the distortions and the areas where the camera has difficulties to use the right signal for the depth calculation. If you activate hardware synchronization, you basically enable the camera or ensure that each camera only emits and receives alternating to each other. And therefore, you can completely avoid the hardware, the interferences coming from a multi-camera setup. Now, last but not least, let's look at some use cases. I've chosen 3 typical use cases where we see a lot of traction in the market. First of all, it's scanning. So using the L515 to scan and create a digital twin of a static object, could also be a moving object. And really here, the high edge fidelity ensures that the objects do not blend into each other when they're close together, and you can really isolate the object that you are desiring. If you look at hardware synchronization, it allows you to build up a multi-camera setup, so you can scan an object with one take without the need to put it on a rotating platform, for example. Additionally, the L515 comes with an IMU and the full HD RGB camera. Together with low power consumption, you can also think of a very robust handheld solution to scan objects. No matter what depth sensing camera or technology you looked at previously, I'm pretty sure you came across robotics use cases. And as initially stated, allowing robots to see and become aware of their environment is really enabling complex automations. Here again, the edge fidelity can make the difference, for example, in pick and place applications where you have small objects that need to be distinguished, or the accuracy over the range can help to detect and identify objects at greater distances compared to other technologies. Warehousing and logistics. There's a dedicated webinar from Intel that you can review on the Intel website that shows a lot of the requirements and some specific use cases where the L515 shines. And again, here, the edge fidelity, the accuracy shine and allow more exact measurements. If you think of box counting for loading or unloading of trucks, inventory monitoring using RGB to scan the barcode, or verifying the correct build of a pallet before you ship it out. This all helps to mitigate some of the typical problems that can be seen in such this vertical. And Intel offers dimensioning and weighing software, the dim weight software, that can help you get a jump start if you have such a use case. As my last slide, let me quickly review some of the specifications. The field of view with 70 times 55 degrees. You have a frame rate of 30 frames per second, very low power consumption of 3 watts. Peripherals such as the RGB sensor and the IMU that allow additional use cases and enable you to project the RGB onto the depth map. High resolution, again, I can only emphasize it's real measurements, it's not interpolated pixel values. accuracy from 5 to 16 millimeter, depending on the range, 5 millimeter at 1 meter, up to 16 millimeter at 9, and an operating range of 25 centimeters to approximately 9 meters. And all in all, the whole camera can be used with the Intel SDK 2.0 as every other Intel RealSense camera. So it's easy if you want to test it and you have an application already built, replace, for example, the D435, put in the L515, and see if you can make better results in your application. Thank you for listening in. I'm curious to see the questions that came in during the presentation.
Okay, thank you so much, Ferdinand, and thank you to all who stayed with us throughout the webinar. If you do have questions and you haven't submitted those yet, please do so by typing them in the question section on your Zoom Q&A panel, and we'll get to them. We do have quite a few questions to get to today, so I'll now pull in Chris, who would also assist us with answering questions. So the first question that I have is, using a scanning laser and a monitoring all the fields can sometimes reduce the SNR. Using an iToF sensor further reduces SNR. Why was this particular architecture chosen or selected?
Yeah, okay. So this architecture was chosen because we had some IP in it already, but more than that, we thought that this was the right choice for a low cost, low power, high performing 3D LiDAR. Keep in mind that a lot of the LiDAR sensors in the market, especially the ones designed for automotive, are planar LiDAR. And those are designed to, let's see, from like 1 meter to 200 meters or even further. That's not the market that this product is going after. The L515 is more focused on several meters of range, but really to have a 3D depth map that's high density. So we had different requirements in those, like those automotive LiDAR products.
Okay, perfect. The second question that I have is the confidence map the same as the disparity confidence? I know that there was some reference to this on slide 17, so.
Sure. Yeah, the disparity is usually used with stereo depth, and the disparity is the amount that a pixel, the difference in the pixel from, let's say, the right frame to the left frame, and that tells you what the depth value is. With LiDAR and with time of flight, it's different. So the confidence is measuring basically it's the size of the peak. So in one of the slides, you were shown like a kind of the noise floor and the peak, and we're using the peak and a couple of other markers that we're looking for to determine how confident the system is in the value that it's sending back. So where you can use this is in certain situations, you may want to have a lot more data, or let's say fill rate. So you can lower the confidence level if you want to, knowing full well that you may have some depth values that have a higher standard deviation than others. And if you're working in a situation where you want to have the most precise Z values you can, and you're okay with having some null values, some holes in the depth map, then you can push the confidence value up all the way. That's how we see users taking advantage of that.
Okay, good. Okay, the other question is, for the detection, are you using any filter to reduce ambient light, or you can completely reduce using such filter?
So yeah, so the filter that we're using is, it's not a super narrow filter, but we're really focusing on 860 nanometer IR wavelength. So the laser diode that we're using is at 860 nanometers. And then the filter and the receiver is obviously focusing on 860 nanometers as well. So we're definitely filtering out any visible ambient light, which is helpful if there's like reflections. Let's say like there's a shiny floor and you're getting overhead light reflections in the floor. The L515 wouldn't see those reflections at all. So that can be a benefit there. Sunlight, however, does have light in broad spectrum, including 860 nanometers. So we're not filtering out that 860 nanometer light, right? We can't tell the difference when it's coming through the filter. We don't know if it's a photon that we sent out and bounced back, or if it's coming from the sun. So we do have a filter. It's focused around 860 nanometer, which means that we can block all visible ambient light and anything outside of that range.
Okay. Another question. Do we need to perform any corrections, rotational, transformational, or transforms in the scan data to compensate for the radial scanning in the corners?
No. So we do that on camera. Although we're originally calculating depth in that radial format, we are doing all the calculations for you so that the information we're putting out is the depth value and not the range value. So the way I think industry and the way that we talk about it is the range value. Think of that as the distance. If you took a tape measure from the camera, you put the tape measure out to 6 meters, and you move that tape measure around, you're making this radial, you're making a sphere, a 3D space that's 6 meters away from the camera. That's not the information that we're outputting. We're outputting depth. And depth is the distance from the imaging plane to the object, not from the sensor to the object. And I realize that can be a little confusing, but the imaging plane is basically, it's an infinite plane that's at the sensor and parallel to the scene that you're looking at. So any information, the depth information that we give is always the depth to that imaging plane. It's not the range, which would be that radial spherical depth construct.
Okay.
If that makes sense.
Another question. What wavelength does the L515 use, and what are the eye safety issues or requirements?
Yeah, so L515 uses 860 nanometer IR light. And it's eye safe, so it's a class 1 laser. There's no requirements to wear safety goggles or anything like that. It's meant to be used in cases where people are walking around and you shouldn't have to worry about where you're looking or how the camera's positioned.
Okay. I'll get to a couple more. So the other one is, what is the typical power consumption, including both sensors and compute?
Compute is a difficult one. The L515 itself has a max power consumption of about 3.5 watts. That's assuming all the streams are at max resolution and everything is turned on. So that's the depth, the color, and the IMU are all streaming. We do all the depth processing in the camera. So no depth processing is required by compute. What compute needs to do at a minimum is to be able to accept the data coming over the USB at fairly high speeds, and then deal with those somewhere. So that could be putting it into memory, it could be writing it to hard drive, it could be doing something else with it. The amount of compute required is really dependent on what the application is. We have customers using RealSense cameras that are plugged into Raspberry Pis, and we have customers that are using i7s. And it really depends on what you're doing with that data after you receive it. It also depends on how much, a a lot of applications don't need the highest resolution that the L515 is capable of. So if there's a concern about the compute needed for a particular application, I'd always suggest, try using the lowest resolution that's good for your application. And then beyond that, something else that can be looked at is lowering the resolution even more after it's received by the host. Could be some kind of decimation or pixel binning or whatever, so that you have the least amount of pixels that you're working on. But the amount of compute really varies from use case to use case. Software, if you're using Python or ROS or MATLAB, it's very dependent.
Okay. I promise I'll do two more. So the other one that I have is the hardware synchronization helpful for removing interference if two cameras face each other? I think this is a really good question.
Yeah, so yes, it absolutely it does. If two cameras are facing each other head on, let me explain what we're doing with the synchronization. Maybe that would help. The cameras, so as discussed in there's a MEMS mirror, there's a laser shining on a MEMS mirror, the MEMS mirror is moving around, and then we have a receiver. What we're doing with the hardware sync is we are turning off the laser. So normally the laser is always on and transmitting on the L515. When we have set up the hardware sync and it's time for that camera to be off, we turn off the laser. So that's how we're eliminating interference between cameras. I wanted to mention that because if the hardware sync is set up properly, even if two cameras are facing each other, you won't have the two lasers operating at the same time, but the camera will still be receiving. I guess what I would say is that my suggestion would be don't have two cameras face each other directly head on without something in between them, without having hardware sync in place. Hardware sync does a great job of eliminating the interference because we're disabling the laser completely. If there's more cameras in the scene than just two, we have a white paper on our website where we talk about maybe some suggestions on how to stagger them so that it's not only one camera on at a time, but you can have multiple cameras on at a time as long as they're not pointing in the same direction. But the white paper goes through some details. I definitely recommend that if you're thinking about using hardware sync, take a look at the white paper that we have at intelrealsense.com.
Okay, perfect. All right, I think I will end that for the questions. Thank you so much for everyone who submitted questions. I know I haven't gotten to a few as yet, but I will get that over to you in the next few days. But just to reiterate, as I said, we'll send you the slide decks, all the links that are in the presentation, as well as the on-demand version of the webinar in a couple days. So keep an eye out for that in your inbox. And also, please don't forget to follow Framos and Intel RealSense on LinkedIn, Instagram, and Twitter, where you'll get more company information, product launches, white paper information, webinars, virtual and on-site events when we do get back to those. So thank you so much again, and we will see you next time. Bye-bye.
Thank you very much.